today, we're going to be discussing our relative motion. And so we'll be going over some of the FreeFlyer 7.6 enhancements, talking about what we've added to FreeFlyer to make relative motion easier. It was possible before, but now we've just made it into a simple, few simple methods for an outside user to use. I'll talk about our HCW Propagator and how that works within FreeFlyer and its equations of motion that it's using. I'll talk about some of our new curvilinear reference frames that we had to apply so that relative motion could be easier in FreeFlyer, as well as some relative motion orbit wizards that we created and their simple setup. And then we'll talk about working with actual relative states in FreeFlyer and how that applies with our new objects and new relative motion enhancements. And then finally, I'll talk about the relative motion utilities object and the power of that. Now, I did want to bring attention to all attendees that you are and will remain muted during the entirety of this presentation. If you have any questions at any point in time, please ask them in the chat box attached with the GoToWebinar, and that will be answered at the end of this presentation by myself, and then of course shared with the rest of our users today. Okay, so first off, we've added a number of enhancements to FreeFlyer 7.6. Some of these we've already talked about earlier in this week, primarily optimization, but there's some others that I wanted to make folks aware of, such as our new plot styling controls. So that allows you to use different color palettes, customize how your plots are displayed, which is a very useful thing for actually giving reports and conveying information. Our new file system enhancements. So we've added the ability to control files and folders. That includes copying, creating, deleting, moving, and renaming. So that now all can be done from within FreeFlyer using simple commands and our file system object. And then some new scripting enhancements, such as adding static constants for mathematical constants and and physical constants. And then, of course, a new diagnostics object, which we've talked about a little bit in our earlier sessions, to improve error handling and reporting so that a user is more informed of what's causing issues in a mission plan. And then if you were here yesterday, we had the entirety talking about optimization and how we were supporting SNOpt, IPOpt, and NLOpt. I thought that was a great presentation. If you did not get a chance to sit in on that yesterday, we do have the links available, and I highly recommend reviewing it. But with all those enhancements, the big one we're here to talk about today is our relative motion enhancement and the power that we've added to FreeFlyer. So now FreeFlyer is going to support the ability to actually model relative motion of a secondary spacecraft with respect to a primary spacecraft using the Hill-Kloetzke-Wiltshire equations of motion. These are our first order derivative equation of motion. They make it easier for us to provide built-in relative motion propagation and which really allows for simpler prox-ops analysis. So this is going to give people the power to actually say, hey, I'm going to do some type of proximity operations, or I'm going to do a close approach of another spacecraft. And instead of having to actually configure all of that via yourself, doing scripting procedures, we've added in this new propagator that's going to handle all of those equations in the back end. To go along with that propagator, we've also added some new curvilinear attitude reference frames, which are going to be useful for the relative motion analysis in both propagating and reporting positions. As well as we've provided 5 new relative motion orbit wizards. So for those that are already familiar with FreeFlyer, there are built-in orbit wizards that we have for setting up simple orbits such as geosynchronous, Molniya, polar orbits, things of that sort. We've now added in orbit wizards specific to relative motion to set up a circular relative motion orbit, an Inplane, an NTrack, a projected circular, or a safety ellipse. And we'll talk a little bit more about that later in this presentation. And then another big one is our relative motion utilities object, which is going to be helpful for a user to configure the initial orbit of a spacecraft that's going to be using relative motion or performing proximity operations analysis. And we can see a simple example of using our new built-in relative motion in this image on the right, where it's just showing one spacecraft orbiting a second spacecraft as that primary spacecraft is being propagated. Now, through the analysis of relative motion, we're actually looking more at the kinematics in FreeFlyer, and that's what it's handling. With the use of these relative motion kinematics, FreeFlyer can obtain the time derivatives of a relative coordinate set. It can get and set the inertial position or velocity of a secondary spacecraft with respect to a primary spacecraft. And it can also provide the ability to evaluate the HCW, or those Hill-Koleski-Wilshire equations of motion, in various relative coordinate systems. And again, we've added some new coordinate systems specifically for this relative motion enhancement. Now, for the relative motion, for the HCW equations, we are using the first order derivative equations for this, and this is due to them being the same form, being able to produce results in the same form, whether you're using curvilinear or rectilinear coordinate systems. So now let's talk a little more about the HCW propagator. We added this propagator specifically for simplifying the relative motion propagation. So this gives a user the ability just to set that propagator and then use our simple step commands to actually propagate using the relative equations of motion behind the scenes, so that you don't have to take into account those when you're actually looking at the spacecraft state position. Now, the HCW equations of motion are defined based on G.W. Hill's initial equations for motion of motion of relative objects in an orbit. And then later on, W.H. Closey and R.S. Wilshire came back and linearized those equations to make them simpler for use today. Now, these equations of motions don't account for disturbance forces. So things such as non-point mass gravitational perturbations or environmental forces, such as your drag and solar radiation pressure, are not taken into account. But using FreeFlyer, you do have the ability to get what we'll say is a general sense of your analysis using these HCW equations of motion. And then if you wanted to go into a higher fidelity, you could do that either using FreeFlyer and some additional scripting, or another program that you can tie in with FreeFlyer using its FreeFlyer API. Now you'll see in the middle of the screen, these are just a basic summation of the equations that are being used by HCW. And our top one is our relative position, where you're just taking the relative position of your secondary spacecraft in relation to the primary spacecraft. And then the bottom one is our inertial velocity, with taking the inertial velocity of the primary spacecraft into account, as well as the angular momentum of your central body. Now, the HCW equations of motion, when they're being used, are only applicable with two general conditions are met. And that is when the distance between your secondary spacecraft and the primary spacecraft is small, as compared to the distance between the primary spacecraft and both spacecraft's shared central body, and when the primary spacecraft's orbit is circular or basically near circular. Now, the reason that we picked these HCW equations of motion and created a propagator for this is because they are the most common equations for relative motion and provide simple solutions. Now, our propagator will also allow a user to automatically propagate that spacecraft relative to another reference orbit and not just a spacecraft. So you can set up an initial orbit and tell your secondary spacecraft that I want you to reference this orbit and propagate in relation to that. It can also reference a state, or when it's also referencing the state, it's propagating the reference orbit using a two-body propagator to apply and adhere to that assumption of a non-point or a point mass gravitational force and non-external disturbances or perturbations. Now, in addition, our HCW propagator can be used with an impulsive burn to model maneuvers. So this can be used to model entering a relative motion orbit or exiting a relative motion orbit, as well as modeling modeling the maneuver just while actually in a relative orbit. Now, When you're using the HCW Propagator, you have two options of configuring it. One can be using our spacecraft GUI, and if you are a FreeFlyer user, you might already be familiar with the spacecraft GUI, which is accessible via the object browser. You can open that up and then go to our Propagator settings page and set the configuration there. Or at any point in your mission plan, you can configure your spacecraft to use an HCW Propagator via FreeFlyer script. So in this slide, we actually see the simple examples of our setup of this HCW Propagator. On the left side is the GUI setup that I was just alluding to in the previous slide, where you access this via the Propagator page of our spacecraft GUI, and then you will set the integrator type to be an HCW. And once that's set, you will see the step size entry as well as this HCW reference orbit definition. And this is the chance for a user to actually set their reference orbit. And again, this is an orbit that will be propagated using a two-body propagator. And define also the coordinate set that you would like to propagate your reference orbit against. And I'll talk a little bit more about that in a second. Now, in comparison, say that you are creating your mission plan entirely in script, or at some point in time in your mission plan, you get to a relative motion analysis portion, you can configure your spacecraft using our simple using the simple script that is shown here on our screen, where you're setting the propagator type to be an HCW. And then we can see that we're just accessing the properties of that propagator using our typecasting, and we can see that we're setting our step size to be 300 seconds, just like we would in our spacecraft GUI. And then we can see that in this script here, we're actually creating a time span and an array to handle our reference epoch and our actual reference state in Keplerian that we want to propagate against. So once we actually configure this time span and set the values in our array, you can go and then you can actually have three options for setting your reference orbit. The first is using another spacecraft, which we talked about earlier. And so you can just set your reference orbit and define a spacecraft object. Or if you were using a reference state, such as this Keplerian state, you can just use that as an overload. Now, when you're using this as an overload, it does assume that the array that's being inputted, or the information, is going to follow a certain order of your semi-major axis, your eccentricity, inclination, RAN, argument of perigee, and true anomaly. If you were to try and input a array that had more or less values or more or less elements than were necessary, you would get an error. And then in addition, you can also reference your Keplerian state at a specific epoch. So to set some reference state to a position you knew a day ago, and then you want to propagate to the current day. You could set your reference epoch to that previous day and that previous orbit that was known, and then propagate within FreeFlyer using the HCW equations to find your current relative state. So FreeFlyer does provide the ability to define the kinematics used to propagate the HCW equations of motion using one of the three coordinate sets. And that is our RIC Cartesian, our RIC Cylindrical, and our RIC Spherical. Now, the RIC Cartesian is considered the classical implementation of HCW formulation, but the RIC Cylindrical and Spherical will also work, but sometimes can provide a more accurate or higher order results. And in some cases, the RIC Cylindrical and RIC Spherical are curvilinear relative elements with the possibility to achieve more accurate results using those same HCW equations. Sorry, said that a little weird the first time. Now, looking at this slide, if you look at the plot on the bottom, you'll see that our Cartesian set differs by increasing over the other two remaining similar sets, which is the spherical and coordinate set. Now, you'll notice that as this is actually increasing, the difference really is not that large. We're only seeing about a difference of 45 meters over a 10 to 12 hour span. So again, we can see that all three of these coordinate sets are providing pretty accurate results and pretty similar results, but you can just get a little bit more higher fidelity by using the RIC cylindrical or RIC spherical. And now we can see here how it's propagating out and updating our difference in position. Now, let's talk more about the curvilinear reference frames that are used by our relative motion analysis. To successfully do this in FreeFlyer, we actually had to add 3 new reference frames. The LVC, which is a cylindrical reference frame, the RIC cylindrical, and then the RIC spherical, which I just talked a little bit about. Now, these curvilinear reference frames are similar to Cartesian frames, but are using a cylindrical or spherical boundary, as we can see in our images to the right, where with the cylindrical frames, it's being defined, being defined where essentially it's polar coordinates, and you are having an r and theta that defines your point on the xy, and then that's projected using our z difference into the cylindrical coordinates. Whereas with our spherical, we are using more of 2 angles and a distance to actually specify the relative position. So in this case, we can see that we have an angle theta or an angle phi or phi, depending on how you pronounce it. And then that's being projected some distance onto our spherical boundary. Now, both of these, again, are helping to make the relative motion a little more accurate in its propagation and its analysis. And so that is why we added them into FreeFlyer. So I wanted to talk a little more actually about these frames in depth. The first one is the LVC cylindrical frame. So the LVC stands for our local, vertical, and curvilinear. And this frame is aligned with the LVLH. So we then have our positive direction of the theta, z, and delta rho coordinates being shown in light blue right here. And then we know that those are going to match to the directions of our LVLH vectors. So in this case, we can see that our primary spacecraft is over here with an LVLH similar form or frame, and that we are translating our position using some theta angle, our delta rho, which is that polar coordinate type of setup that I was talking about, where we're projecting into the XY plane. And then we actually are then traversing our Z to find the actual relative position of our spacecraft. Now, if you did not want to use the LVLH frame, and you are more familiar or more comfortable with the RIC, we also do provide that RIC frame for our relative motion curvilinear reference frame. And this is where we have our RIC cylindrical frame being aligned with the RIC Cartesian frame. Therefore, we have our positive direction of the delta rho, the theta, and the z, all matching the direction of our RIC vectors, which we can see in our image here, where our x-axis is our r vector, or the radial. The y-axis is our NTrack, which is the negative of the r and c crossed. And then our z-axis is our c, or cross-tracked axis. Now, with this, when we are defining our relative position using the RIC cylindrical, we're again using those polar coordinates translation, where we travel some angle theta and then some delta rho for projection, and then we actually project into our z-axis for the position of our secondary spacecraft. Now, in comparison, our RIC spherical frame is also aligned with the RIC frame. Therefore, it has the same positive direction for its delta r, theta, and phi angles, or phi, and shown in light blue. And with this, it differs slightly from the cylindrical, as in the way that we are actually translating our position. So on the cylindrical, we saw that we had that projection of the delta rho into our XY plane. In this case, we're using a theta to find our translation of the angle, and then we're using a phi or phi to actually traverse up our spherical boundary, and then we take the difference in our relative position, in our radial position, to actually define that relative spatial reference. So Again, these are just using the same RIC reference frames that most folks have used in the past. The only difference is that they are traversing the relative position either using a cylindrical boundary or a curvilinear, or sorry, a cylindrical boundary or a spherical boundary. Now, next thing I wanted to talk about is one of the things that I think is a great enhancement for our relative motion orbit wizards. These will actually allow a user to quickly configure the orbit state for a secondary spacecraft with respect to its primary spacecraft to create an orbit in any one of the following types. So circular, Inplane, NTrack, projected circular, safety ellipse. We see all 5 of those orbits in our image here to the right. And again, these were all created by using a simple one-line method to set up that orbit, and then by just doing a simple propagation loop where I'm stepping my spacecraft over some amount of time. There's no additional configuration, no additional calculations or analysis that you have to do to ensure that this orbit stays stable during your propagation. You just set it and then go. Now, a big note is the relative motion orbit wizards are only accessible via the FreeFlyer scripting language, and they're accessed directly from a spacecraft object. So we did this to just make them similar to our previous orbit wizards, which are all accessible via the spacecraft object, where you call the spacecraft, the desired orbit wizard, and then input the required arguments to set up your orbit. So we're going to take a little bit more of a closer look at some of these orbit wizards and what they're doing. So the first is our circular orbit wizard. In this case, our secondary spacecraft is going to fly in a circular orbit around the primary spacecraft, where the orbit is defined by a radial separation and some initial phase angle and inclination psi. So the initial phase angle is basically your inclination in relation to your XY frame, and then the inclination angle will determine if you are in a posigrade or retrograde orbit around your primary spacecraft. And if you were to go and actually plot this out, looking at our radial NTrack or the radial versus NTrack, and then the NTrack versus cross-track plots, we can see that this is setting up a simple circular orbit that is following around our primary. And of course, with this radial cross-track plot, we can see the inclination that's being applied, where it's going above and below the XY plane at times during the propagation. The next one is our Inplane orbit wizard. So this will set up your secondary spacecraft to fly in plane directly with the primary spacecraft. Now this orbit is only defined using the Inplane separation or your long track separation. And as we can see in our GIF here, that our in-plane orbit is basically staying perfectly aligned, or is staying perfectly aligned with this XY plane, and in this case our Y-axis, because we're only doing our long track separation. And then if we were to plot this out, we could see that this is keeping us at a relative position that is exactly in plane with our primary spacecraft. So another simple setup. Now our next one is the NTrack orbit wizard. And this wizard is used to, or is just done for an NTrack orbit with your primary spacecraft, where you're defining the in-plane separation and the cross-track separation. So we can see here in our radial versus NTrack plot that we are staying in plane during this time, but we are actually having some rise and fall of our in-track cross-track as our spacecraft is staying in track using this orbit wizard. Now, some might ask, what's the difference between or reason you would use an in-plane versus an NTrack? And the reason is that with an NTrack, you can actually set this up to maintain the same ground track for your spacecraft, and this is done, specifically just to, if you wanted a spacecraft that was going to look over a specific area, and you wanted to ensure that its ground track was staying aligned, while also using relative motion in reference to another spacecraft, this simple orbit wizard would be easy to set that up. Our next one is our projected circular orbit. Now, this will just project a circular orbit around the primary spacecraft, where your orbit is defined using a radial separation and then initial phase angle and an inclination angle. So similar to our circular orbit wizard, the main difference is that with the projected circular orbit wizard, this causes your secondary spacecraft to revolve around the primary spacecraft in an ellipse, where the relative trajectory formed from that is a circle projected onto the primary spacecraft's RIC frame in the YZ plane. So your NTrack cross-track plane. And we can see that right here, where our radial NTrack plot is a little bit of an ellipsoid or oval, versus our NTrack and cross-track plot, which is giving us circular results. The next and our fifth orbit wizard is the safety ellipse orbit wizard. This provides the ability for a secondary spacecraft to fly in an ellipse around the primary spacecraft, where all you have to do is define your radial offset, your cross-track max distance, the center of your ellipse in the NTrack, and then the center of the ellipse rate NTrack, as well as your phase angle and radial motion. So we can see here that this is done with this simple setup: our radius, our cross-track, center of ellipse, rate and track. And when we do this and we provide a 0 rate and track, we can see that we get a perfect safety ellipse that is flying around our spacecraft, our primary spacecraft, and keeping the cross-track max distance and the center of ellipse and track as the same position. But if you would like, you also have the option of setting up what is called a walking safety ellipse. Now, this can also be configured using that exact same method, but by setting a non-zero center of ellipse rate for the NTrack. When we do this, we can see that our spacecraft is starting at a position and is actually propagating using this safety ellipse orbit, but as it's propagating, it's also walking based on that ellipse rate of NTrack, either away or towards our spacecraft, our primary spacecraft. And in this case, it's walking away, and is just creating is maintaining the safety ellipse orbit while also creating a greater distance. And we can see that being also shown here in our plots, where we have our radial NTrack plot showing the safety ellipse, and then our NTrack cross-track plot showing that it's actually walking away. And then of course, when you actually look at the radial and cross-track, it actually generates the ellipse that's being orbited. All right, the next thing that we are going to talk about today is our relative states. So FreeFlyer, we've not only added the HCW propagators, but we've added enhancements to handle and work with relative states. Some of these are used to identify the position and velocity of a secondary spacecraft relative to a primary spacecraft. And we've also added the ability for setting and reporting the relative state of another spacecraft in motion, or in a relative motion. Now, these states for setting or getting can be classified using either the local Cartesian or curvilinear states, or by defining a relative position and velocity in any one of the available reference frames shown on the right. So our MJ2000 is typically the default frame for the majority of properties. Our VNB is the most common frame when implementing a maneuver, and then our others such as LVLH, LVC, RIC, UVW, geodetic, and your body coordinate system. All of these are available to be used with these methods that are shown at the bottom of this slide, whether they are Cartesian states or curvilinear states. You can just simply call this from their spacecraft object. And if you wanted to set the position, you can just simply call set relative Cartesian or set relative curvilinear state. and then give a reference spacecraft because we need a reference orbit, and then provide an array with that state for either for your position and velocity that you want relative to your primary spacecraft. And with that, you will then be able to set your spacecraft, set it and forget it of saying, hey, I know that it is 10 kilometers in the NTrack moving at 1 kilometer per second because I use this method with my array state. Vice versa, you can also report your current curvilinear state or Cartesian state by just calling the spacecraft with this method and then referencing another spacecraft so that it can define where its center of origin is going to be. By using this, it will report out both the position and velocity. However, if you did not want to do the full state, you just wanted to report your position or velocity, both of those methods are available for the Cartesian and curvilinear states. As a note though, if you are using, or if you were wanting to, report the position the position and velocity for the body coordinate system, you can only use those methods. The curvilinear state will not actually take a body coordinate system as an input argument, nor will the velocity, just because again you're referencing it to your spacecraft's body coordinate system. All right. One of the other things that we've added to FreeFlyer for our relative motion enhancements is the relative motion utilities object. So this is a built-in object into FreeFlyer that users do not have to set up. This will actually provide the ability to do static methods for predicting the future state of a spacecraft that's using HCW's equations of motion, computing the required delta V vector for a spacecraft to achieve a future relative position using those same equations of motion, or convert a current relative state between different relative motion reference frames. Now, this object, the object methods will accept either a secondary or primary spacecraft, as well as the relative state and the primary mean motion. We can see here on this bottom example, this is just a simple implementation of our relative motion utilities object. So we see that we have two spacecraft. We set a relative Cartesian state using a reference spacecraft and then an array for our position and velocity. And then again, without having to actually create this object because it's already available, we can just report the compute state for our HCW at some future time. We can convert and get a relative state based off of the primary spacecraft's mean motion. We can compute that delta V, where we are either doing it via a specific state or future state that we want to achieve over some time, or a relative state using that mean motion. And then of course, just converting our relative state, our position, or our velocity, where you can input the reference frames that you want to use for the input and output, as well as the relative arrays that you're using for defining your secondary spacecraft with respect to the primary spacecraft. So again, all of this is built into FreeFlyer. You don't have to create it. It's simple object to access and use, and provides a lot of power and flexibility, especially when you are configuring or evaluating when or how to maneuver into a relative state. So now that we talked about that, let's take a quick minute and we're going to flip over to FreeFlyer. And I actually want to open up one of our sample mission plans that is available for users to review. All right, so this is the home screen of FreeFlyer. For those that are not familiar, this comes up anytime that you open FreeFlyer and provides a quick access to some of our demonstration mission plans, as well as sample mission plans that are showing our new features added to FreeFlyer. You can see here that we have a number of new sample mission plans that we've added for both relative motion and optimization. I highly suggest when you have the chance looking through these. They're great resources. And also, we always encourage our users to feel free to use these as a base or a stepping stone to creating your own mission plan. So please feel free to open these up and then review them and then start updating or using them how you see fit. In this case, we're going to look at our proximity operations with a head track mission plan. And what this does is this is showing that we have a secondary spacecraft that's being propagated using HCW motion, the HCW motions of equation in relation to a primary spacecraft. And in here, this blue portion is defining our previous or actual propagated spacecraft orbit. And then this white portion is showing, using a graphic overlay, our predicted or a head track orbit using our built-in relative motion features. So this is just a simple setup saying, hey, I want to propagate with relative motion, but during that time I want to see where it is. And then at some point, such as right here in our mission plan, we want to initiate a maneuver to actually put us into a semicircular orbit and around our primary spacecraft and then propagate. And we can see over here in our console window that it's reported out what is the required delta V to actually initiate this orbit. So again, this is a super simple setup with our new features and our new built-in objects that make it very easy for users to go ahead and just jump right into relative motion analysis and proxops, basically proxops operations. Now, if we were to flip over to our control screen and we look, we can see that our sample mission plan here was set up using only freeforms, and that in this freeform, we've set up our primary spacecraft to use a two-body propagator, but our secondary spacecraft is using the HCW equations of motion, where we're setting that reference orbit just using our primary spacecraft and then setting our step size. And then finally, we're actually setting an initial relative state for our secondary spacecraft using our built-in orbit wizards. And in this case, it's the safety ellipse orbit wizard. So this is the entirety of setting up our initial relative motion and the orbit that we are going to be using for that relative motion and what we saw in the beginning. And then as we propagate, we eventually are getting to a point where we're going to compute our delta V to put us into a relative motion orbit that reaches a desired location or future state. And that's being done again with this relative motion object or relative motion utilities object, where we're computing the delta V using those HCW equations of motion, and we're setting a future state that we want to reach, and that is then giving us this predicted delta V. Once we get that predicted delta V, we can just input that in using a impulse burn, which is what has been done here. We can see that the burn direction is just being set directly from this array, and then we maneuver our secondary spacecraft to enter us into that relative motion orbit. So again, all very simple setup, and then again, once we get in there, the rest of this is just basic propagation, where you have a loop. In this case, it's a while stepping loop, and we are stepping our spacecraft, and then we're doing a procedure in this case, but we're also updating our view. So simple setup, very easy, not a lot of configuration requirement during the propagation that is going to be necessary on the user side. Simple set it and forget it almost. Okay, so now that we looked at that actually is wrapping up our relative motion session today. Now, with all that said, I'd be happy to take and answer any questions that might have come up during my presentation.
Can you convert relative states between reference frames, or are you tied down to one reference frame for your whole mission plan?
No, you can convert your relative states between any of the available reference frames. And in fact, I mentioned it a little bit earlier, but let me flip back. We actually have all of these reference frames that are being shown. Oh, sorry. All of these reference frames are available for converting relative positions. And again, you actually use these methods here. There's an additional argument that can be added to either one of the or to any of these methods to actually define the relative reference frame that you want to output your relative state. So we have that built in, very simple, easy to use.
That's great. So this one is a little bit open-ended, but can you use this capabilities, these new enhancements, to plan maneuvers?
Absolutely. So you can definitely use these enhancements to plan impulsive burns to either enter you into a relative motion orbit or exit you from a relative motion orbit. That can be done with the relative motion utilities object and using the compute delta V HCW method, and then just providing the necessary arguments. So very, very easy, very simple. And again, if you wanted to do this maneuver in another reference frame, you could also use the relative motions utility object to convert between those reference frames before actually computing the delta V.
Okay, great. So this question is related to the missions that FreeFlyer is supporting right now. And what somebody was focused on our session yesterday, and they're asking, are these capabilities being used for OSAM-1 or for ISS or the Dream Chaser or the other missions that FreeFlyer is currently operating or is building a dynamic system?
So I can say that I do know there is current users that are performing relative motion operations using FreeFlyer, but more than likely they're still using older versions where they're doing it by hand and procedures. Since we just released this last month, we have had missions reach out to us about updating and upgrading their code to use these new features. So I know that there's people that have plans in the work to start using these with their current mission plans. And I do believe OSAM-1, when I was talking with some of their members, was already looking into possibly adding this before they go to operation so that they can have simpler relative motion operations.
Yeah, and given that we just released 7.6 just a few weeks back, so it's probably taking them time to rewrite some scripts or make these improvements. So before we get into the few remaining questions, I would like to remind everyone again, we have 10 minutes. We can answer any more questions you have about FreeFlyer, about features or capabilities or licensing. Just let us know. So Craig, can you use the orbit wizards with high fidelity force models, or do you have to use the HCW Propagator?
So you will have to use the HCW Propagator with with the orbit wizards to ensure that you're actually getting the proper orbit. You do have the option of using a force model with this, but again, the orbit wizards are assuming that you're using an HCW propagator during the propagation portion.
Okay, that makes sense. So this is coming from one of our users who's already been using the existing pre-7.6 FreeFlyer capabilities for relative motion analysis. Now, do the message that you mentioned here, is it worth upgrading from what he has to 7.6 and rewriting these scripts?
I will say absolutely. It is definitely worth upgrading it. And I can say this personally, where for my Kara position, we actually are going through that process right now. JSC actually has some FreeFlyer mission plans that perform close approach analysis or collision on launch analysis or COLA. And then once it actually gets to basically some relative height, it can actually do relative proximity operations. So we're updating that to use the new 7.6 features, as well as I've seen some folks already reach out to us and start asking like, hey, is this worth it? And if I can, or if it is, do I need to update and change anything in my script? And for those folks that we've looked at, we can see that we've definitely decreased their script by a large number of lines. Because again, you're taking all of these equations for calculating your relative position, figuring out the relative velocity, and then converting, your angular momentum, things of that sort, normalizing it all. That's no longer needed or necessary. It's all being done by the built-in methods and single line methods, or built-in objects and single line methods.
Awesome. I think that's going to encourage a lot of people to start looking into upgrading to 7.6. So we have more questions coming through. What are the static methods? I know you touched on that a little, but can you talk about it more?
Sure. So our static methods are the methods that are available to the relative motion objects or the relative motion utilities object. Right, sometimes gets there. But the static methods are just our compute state HCW, the compute delta V HCW, and then those convert relative state and convert relative position and velocity, as shown on the screen over here. These are just simple methods where if you call this relative motion utilities, and then you look through what is the associated methods, all of these are available. You can just call them up and then input your necessary arguments. And then in this case, you can see it's just reporting it out directly to a console. But if you wanted, you could save it to an array, to a variable, whatever it's outputting, and then use that later on in your mission plan.
Okay, perfect. So this question is related. We're going to be talking about lunar missions tomorrow. That's the main topic for tomorrow. But this one is, can you use this capabilities for relative motion for lunar orbits as well, or is it just for LEO or GEO or near Earth orbits?
No, you can use it for any orbits you would like. The only catch, or the only assumption by the HCW equations of motion, is that your spacecraft, your primary spacecraft, is in a circular orbit, and that the distance between your primary and secondary spacecraft is no larger than the distance between the shared central body. So just to note on that, when you are using this, our HCW propagator, it does assume that the primary and spacecraft both have the same central body. So in your case, if you wanted to use a lunar relative motion orbit, as long as they are both using the moon or both using the Earth while they're both using the Earth as a central body while they're around the moon, there will be no issues.
Okay, fantastic. So while talking about the HCW propagator, this question is about its precision. Now, how precise is it relative? How precise this HCW propagator is relative motion features while using gravity assist maneuvers?
So that I would have to look into. I have not done any testing with the relative motion while performing a gravity assist maneuver. But overall, the HCW propagator is pretty accurate. When we add new features, we go through a large amount of testing and validation because we always want to ensure that we're putting out a good product that's going to give an accurate answer. So we know that overall it is accurate. And again, depending on the coordinate set that you're using for propagation, you can increase your accuracy. However, we saw that it was on the order of just a 45-meter difference between our RIC Cartesian versus the RIC spherical and cylindrical. So not a very large difference. Of course, when you are getting into close relative proximity operations, that might take a little more, might have a little more weight into what you're doing. But I can look into the gravity assist and try and get an answer back to you.
Okay, yeah, and as we mentioned earlier, every question that comes through there during this or any other Q&A session, we're gonna follow up with you in more detail, and we're gonna be communicating until you have like a tailored answer, because we might not have an opportunity now to spend 5-10 minutes for every question. This is a comment, but it's also an opportunity to hear your thoughts, Craig. So one of our users is saying that they plan on using these modeling relative motion features for multiple secondary satellites that will be launching with one of the upcoming missions. That is something that you can do, right?
Absolutely. So again, you can do as many spacecraft as you want in a relative motion orbit, as long as you're just defining a primary spacecraft. So if you wanted to have 10 spacecraft that are revolving around one single primary spacecraft, that's simple to do. You can do it. You can set it up where you are using individual spacecraft or a formation object and then propagating them, propagating all the spacecraft in that formation using an HCW propagator. Now, actually, I guess we didn't include a sample mission plan for formations, but I know we have done it internally where we've propagated more than one spacecraft in relation to a primary spacecraft and had no issues, no hitches, no additional like super special configuration or coding that had to be done. It was just creating the relative spacecraft and setting them all to use the same primary spacecraft as a reference orbit.
All right, that's clear. So going back to the question that was before this regarding the precision of the HCW propagator while using a gravity assist maneuver, our developers were just looking at this question and we have more details to share. So the HCW relative motion propagator assumes a circular orbit. Given that gravity assist maneuvers are performed in highly elliptical orbits, there will be some inaccuracies. So we can talk with the user about this more if that's something that they want to use in the future. But that's the answer that we have from our development team, and we'll dive into it later.